Welcome to part 2 of the Wild Horse Wind Facility virtual tour. We're going to start moving through some of the components that we would see on our regular tour. What you're looking at right now is the gearbox. It weighs 17.5 tons and it's one of our most expensive components, but it has a really important job. Its goal is to speed up the very slow blade speed. As you can see, the turbine blades are doing about 16.5 revolutions per minute. The gearbox speeds that up to over 1,800 revolutions per minute, and it does that through a series of gears. Right here is where the blades would actually attach through the main shaft and bearings. This larger round section is the planetary gear set. And then we move on to this side of the gearbox where we have helical gears. And their job is again to speed that slow rotation up to over 1,800 revolutions per minute. Inside you can see one of those helical gears on the high-speed stage. And this is where we would have the high-speed shaft. It would connect over here to our generator. From here, once that gets rotating, we'll look inside to the stator and the rotor. The stator is the copper coil you can see on the left-hand side. The rotor is just underneath that. That's the part that rotates, and I will show you how that works. Once the winds have reached at least 9 miles per hour, the generator will be spinning fast enough to create electricity at over 1,800 revolutions per minute. At that point, the magnetic fields within the generator induce a current or start pushing electrons through the copper coil. Once we've converted the rotational energy created by the wind into electrical energy, that energy is transported from the generator, from these 4 cables. You're going to have to imagine those, but they would run to the back of the nacelle to the transformer. The transformer's job is to change the voltage from 690 volts to 34.5 kilovolts. So higher voltage electricity travels more efficiently, and we can also use a smaller cable to transport that electricity. From here you can see the rest of the project. Some turbines are waiting for more wind, some are running, and some are offline for maintenance like this one, where you can see its blades are turned backwards out of the wind. Technicians climb these every 6 months to make sure they stay operating smoothly. Now we'll move on to the blade. Let's go take a look inside. Inside of the blade we get some amazing echo! You can also see the lightning ground cable on the left-hand side, which pops out the surface of the blade on 5 different points called lightning pucks to ground the electricity from a lightning strike through the blade and into the foundation. That way our blades aren't damaged during electrical storms. Now let's take a look at the outside of the blade. At Wild Horse we use Vestas V80 wind turbines, which have an 80-meter diameter wingspan. Each individual blade is 39 meters, not counting the hub, which is 128 feet long. These blades weigh 14,000 pounds and are made up of 3 pieces, 2 outer shells that give the blade its shape, and an inner spar that strengthens the blade. The edge we're walking along now is called the trailing edge, and it's quite tapered and sharp. That's why we call these blades. And we're heading down to the opposite end. Modern turbines actually have blades that are twice as long as these, and they can make 4 times as much electricity. Now that we're at the other end, you can see how thin and tapered the trailing edge is. And you can also see the rounded leading edge. These blades are designed after airplane wings originally, and they're an airfoil in shape, which means they have a slightly different shape to their top and bottom edges, and they can create lift as the air goes over and under them. This makes them more efficient than if you just used a flat blade. Older wind technology, like this air motor windmill that was designed to pump water from underground, utilizes numerous lightweight metal blades. Once we start looking at larger technology like these Vestas V80s, we have to take into account the weight of the blade and also the cost. We want these to be efficient strong, and make the most amount of electricity for the least amount of cost.